Swayam Prabha. Digital India. Educated India.
So, in the previous lecture, we looked at effects of low turbulence Reynolds numbers. Now, this low turbulence Reynolds number can occur close to the wall, that is one type of situation, but it can also occur along the length of a flat plate where the boundary layer is growing, where the laminar flow turns turbulent through an intermediate region, which we normally define as the transitional region. And in that transitional region again, the turbulence Reynolds number would tend to be low, and therefore, the models that we just discussed are very much applicable to such situations. But as I said, these turbulence models with roll turbulence Reynolds number require fairly heavy computation expense because of the very large number of grid nodes required close to a wall. And therefore, at earlier times simpler approaches to modeling transitional regime were adopted, and my purpose in this lecture is to really look at laminar to turbulent transition in a little bit more detail. The second issue concerns rough wall. So, much of our discussion till now has been about smooth walls, but in engineering, in order to enhance heat transfer, we often employ rough walls, deliberately structured or naturally rough walls, and we want to see how to capture the effect of a rough wall either in a wall function or ultimately in generating the universal law of the wall for the inner layer of a turbulent boundary layer on a rough wall. And finally, we will look at like we derived the universal velocity law for the inner layer, is there a temperature law for the inner layer, and that is what we will, these are the three topics we will take up in this lecture. So, for example, in a duct, when Reynolds number based on hydraulic diameter, or in an external boundary layer when the Reynolds number based on actual distance x is increased, laminar flow undergoes transition before turning into fully turbulent one. This transitional Reynolds phenomenon actually occurs over a range of Reynolds number, although in the undergraduate work we often believe that laminar to turbulent transition is very abrupt, but actually the transition occurs over a range of Reynolds numbers. Although the range is very small compared to the normal values of fully turbulent Reynolds numbers that we normally encounter, but nonetheless the range exists, and we are going to account, we want to know how to account for that range. The lower end of the range of Reynolds number indicates end of laminar conditions, whereas the upper limit of the range signifies establishment of fully turbulent conditions, and both F and Nu demonstrate unique features in the transitional layer. For example, you will recall that the friction factor in a pipe, for example, decreases linearly in a up to Reynolds number of, let us say, about 2300, and then the friction factor actually increases a little to say till about Reynolds number of 5000, and then the so this is the fully turbulent, this is fully laminar, And in the transitional region here, the friction factor Reynolds number relation is quite reverse of what happens in the laminar and turbulent regions, in that friction factor actually increases with Reynolds number, and therefore, this curious phenomenon needs to be explained in somewhat greater detail. Now, many heat exchange equipment operate in the transitional region, particularly in process industries. This is often found that the Reynolds number inside the tube is often in the transitional region. Similarly, on a gas turbine blade, the pressure gradient varies in the range as low as -10 to the -8 to of this parameter rho by u infinity square du infinity by d by, to as high as 10 raised to -5. Both these are considering both pressure side and the suction side, and the free strip turbulence intensities vary from as low as 2% to 10%. Now, in these conditions, transitional range of REX may well occupy as much as 50% of the chord of the blade. What is meant here is, for example, in a flat plate, initially you will get laminar flow, and then a small transitional regime with X, and then X transition N, and then you will get a turbulent boundary layer. So, this occupies a much smaller length of the total length of a boundary layer. But on a turbine blade, this is the chord, this is the chord length, and you could get transitional Reynolds number as a transitional range occupying almost 50% of the chord length. So, that is why we need to study turbulence somewhat in a transitional region in somewhat more carefully. So, now let us first of all get our ideas of transition in a pipe flow cleared. So, in a pipe flow, if for Reynolds number 2300, F increases with Reynolds number, and if you were to measure u velocity at a fixed point in the flow at any radius of the pipe, then you will see a picture something like this. A flow will be show turbulence for a while at a point, then for a certain period it will be quite quiet or laminar like, then it will be turbulent again, then it will be very quiet again, then turbulent, and then so on and so forth. If we measure this for a certain total time and divide this time period equally in steps of delta t, then in each delta t a small fraction of it, delta t sub t would be occupied by turbulent patch. Likewise, here this much would be the delta t t, whereas this is the total is delta t. Now, we define intermittency as so intermittency itself is defined as gamma delta t of turbulent patch divided by the total time step delta t, and this would be the kth patch, let us say, and then if we sum up all this over k equal to 1 to n time steps and divide this by n, then that is called the intermittency. This is the intermittency definition. It tells you about the fraction of the time for which the turbulent patches occur. Now, obviously, it can only be vary between 0 and 1, and that is what I have shown here, that intermittency gamma would vary from 0 to 1. Now, of course, it would the value of the gamma would vary in a pipe flow from axis to the wall at different points, but usually we speak of some kind of an average gamma. So, we do not worry about the radial variation too much. Here is what I show the value of average gamma versus x by d of the pipe flow at different actual distances. This is the measurement made at Reynolds number of 2300, and you will see that the intermittency does not exceed 0.2 even after going well beyond 500. So, in this case the flow will never turn turbulent at all in practical lengths of pipes, which would be usually 100 D or 200 D at best, but flow will become fully turbulent at very long distance from the entrance. At 2400 x by d of 500, it has reached about 0.4, but at 2500 you will see it has reached about 0.8, and at 2600 it has reached almost 1 at x by d of 500. Now, if you had a Reynolds number of 5000, then of course, it will reach the fully turbulent gamma equal to 1 in a very short distance, and it is such flows that we say are turbulent right from the inlet itself. Between 2300 and 5000, the transitional flow will continue for all practical lengths of the pipes, but for 5000 and above the flow will be turbulent right from the inlet itself in a pipe flow. Similarly, if you were to look at the external boundary layer, you will see the flow is coming from the left, then there will be laminar layer here with gamma equal to 0, but then from here to here, which is the start of transition to end of transition, intermittency will go on increasing with distance. How it will increase, we will see shortly, and then fully turbulent conditions will be reached here at gamma equal to 1. Pictorially, if I were to look at the plan of this, it will look like this. If the flow is coming in from here, you will get very steady flow up to start of transition. Then occasional spots of turbulence will be seen and then tend to grow, engulfed by laminar fluid, which kills the spots. But it is this energy transfer which gives rise to new spots of turbulence, and they would grow, but they are again engulfed by laminar fluid, surrounded by laminar fluid, and therefore they get killed. But the process of energy transfer creates more spots and so on and so forth, and ultimately they grow not only in number, but also in strength, and ultimately at the end of transition you will get a completely turbulent boundary layer or the turbulent fluid. So, the transition is identified with the occurrence of intermittent turbulent spots surrounded by laminar fluid in an external. This is quite visible. You can do a flow visualization experiment to see this. Variation of intermittency with X in a boundary layer has been correlated, and one of the first correlations was by Rodam Narasimha, an Indian scientist working at Indian Institute of Science, and it was 1 minus exponential of minus 412 beta square, where beta itself is a dimensionless quantity, x minus start of transition, divided by x, where the value of intermittency is 0.75, minus x, where the value of intermittency is 0.25. Now, this is of course very well to use in an experimental setup, because you can see where the intermittency is 0.75 and 0.25, and therefore determine the denominator quite exactly. Computationally, this is not very convenient, and therefore more recently in the 80s, Abugunam and Shaw have come up with this expression, gamma equal to 1 minus exponential of minus pi times xi cubed, where xi is x minus xts divided by end of transition minus start of transition. So, all that remains is finding ways to determine xts and xte, and there are several suggestions. So, for example, for determining start of transition, where there is a sudden departure in laminar variations of delta Cfx and stanton x, one can Sibesi is one author, Fraser is another author. So, Sibesi has suggested that at transition, at the start of transition, the Reynolds number based on momentum thickness delta 2 is balanced by this expression, where the Reynolds number x is based on start of transition. So, what one does is if you were doing, let us say, applying integral method, or then during the laminar flow you will calculate Rex and Re delta 2 and see whether that expression that I showed you is actually satisfied. You will see at a certain point XTS, the Rex and Re delta 2 would be related by this expression, and that would identify the start of transition. On the other hand, this expression of course does not take into account the effects of turbulence intensity, which can vary quite a bit, particularly in gas turbine and compressor applications. And therefore, Fraser has suggested this formula, Re delta 2s is related to this Fm and turbulence intensity Tu, and M is the pressure gradient parameter and includes du infinity by dx. So, when this equation you go on calculating Re delta 2s, and when it matches with this for m greater than 0 and m less than 0, then you say that is the start of transition. M equal to 0, of course, make it Fm equal to 6.91 itself. If turbulence intensity is not accounted and taken at 0, then this is simply exponential of 6.91 plus 163, and you take the value of XTS, where Re delta 2 is 163 into exponential of 6.91 for 0 pressure gradient boundary layer and turbulence intensity equal to 0. But for all other cases, the XTS must respond to the pressure gradients. Now, how about end of transition? For end of transition, you would say you define Re sigma as u infinity xte minus xts divided by nu. So, it is based on the transitional length, if you like, Re sigma. Re sigma naught is a function only of the turbulence intensity. 4.6 into 1 plus 1710 m raised to 1.4 into all this. Of course, this term is valid only when m is greater than 0, which means that term is negative, and that would occur in an adverse pressure gradient. We can locate the end of transition in the adverse pressure gradient, as would be expected. So, this is the recommendation of Fraser and Milne, and the paper was published in 1986 in Institution of Engineers Proceedings. There is another recommendation, and that is by Sibesi, who say that Re sigma, which is based on transitional length, should be when it equals 60 times Re XTS, which was identified on the previous slide, Re XTS raised to 2 by 3, then that would signify the end of transition. And then there is yet another one, which is by Deutsch and Zirke, which again does not take into account turbulence intensity, but they recommend that the end of transition, Re delta 2 at end of transition should satisfy this expression, where now instead of m, which was based on like m, which was based on delta 2 square du infinity by dx, here also you see this is really m, 1 plus m at start of transition. So, that is the most important part. This is at the value of start of transition. So, there are 3 expressions, particularly in adverse pressure gradients, all of these work very well. If you wanted to use the integral method for solution of the integral equation through the transitional layer, you would need u over u infinity in the transitional layer. Now, simply by observing how the experimental data look like, So, this is u over u infinity divided by y given in inches here. In the transitional region, the profile would go something like that. As the Rex increases and here Rex increases in this fashion, and finally, you would end up with a fully turbulent profile like that. In u plus y plus coordinates, it would appear something like this, and it is quite customary therefore, to say that u over u infinity at transition would be 1 minus gamma times u over u infinity laminar plus gamma times u over u infinity turbulent. So, having identified the values of x t s and x t e, you can determine the gamma distribution with respect to x, and therefore, you can use this formula, and this is pure pragmatism. There is no big theory, but it seems to work, this kind of pragmatism, and actually predicts transitional boundary layer quite well in using integral method. So, now we turn to how to account for effect of wall roughness. Now, effect of wall roughness, as you will recall even from your undergraduate days, when the roughness height divided by the diameter is 0.001, then we say that the tube is smooth, and you will get this kind of profile for smooth pipe, turbulent region. But, and this would have the height roughness YR of D less than 0.001. But if you increase YR by D, then you will remember that you get friction factor which goes on like that. So much so that you may even get that, and this is where the roughness is increasing. So, the effect of roughness is to enhance the friction factor or the pressure drop, and this is what is observed in experimental data that you will recall from your undergraduate days. We want to explain what are the other features of rough surface. For example, a cement pipe is quite rough, quite naturally, but many a times as shown here. So, it will have a jagged surface. Experimentally, such a surface is produced by pasting sand grains on of various sizes on a surface of equivalent or average height y sub r. But many times we actually have a rough surface which is deliberately structured by providing ribs, for example, like this, or studs, three-dimensional studs can be provided of width w and pitch p, and it becomes quite difficult then to develop any universal law for surfaces like this. So, in order to circumvent this difficulty, what is done is we always take sand grain roughness as a benchmark and determine the friction coefficient for that, and for a structured surface, if the friction coefficient agrees with that of the sand grain roughness, then we say that the structured surface had an equivalent roughness height equal to the sand grain roughness height. So, sand grain roughness are done in a laboratory measurements and they provide the benchmark. What we would expect is near wall law to be u plus now to be not only function of distance from the wall y plus, but also the y r plus, the roughness height. And since we do not expect much of a laminar contribution, we will essentially have a turbulent layer developing, and therefore, we expect that u plus would be 1 over kappa ln y plus c, which would be function of the roughness height y r plus. Usually, laminar sublayer does not exist when y r plus is greater than 70, and we say such a surface is fully rough surface. but if YR plus is less than 70, then you can still get effects of viscosity present, and we have to account for those. So, that is what we have done in the next slide. So, here is a plot of CR, which is a function of YR plus, and the sand grain roughness data was generated by a person called Nikuradze, a very well known scientist from Soviet Union, and it is quoted, this data is quoted in the book by Schlichting called the boundary layer theory, about which I mentioned even during the laminar boundary layer discussion. So, you will find CR versus log 10 of YR plus, when it is perfectly linear and rising, it's a perfectly smooth surface. YR plus itself is very, very low, and therefore, it is not really a rough surface. So, we say up to here the surface is smooth. Then the effect of roughness begins to come in, but CR would then decline, and up to about say log YR plus to the base 10 of about 1.8, which is really YR plus about 70. And then it is found that the experimental data remains really constant with increasing YR plus. So, this is taken as the indicator of the fully rough surface, and CR value for that is 8.48. So, for a discrete roughness, equivalent sand grain roughness YRE is defined, and we say U plus will be equal to 1 over kappa ln y by YR plus CR dash, and the equivalent roughness height then would be YR exponential kappa into 8.48 minus CR dash, where CR dash is a function of the width of the rib or the pitch of the rib, and is determined experimentally. So, that is how one would get the universal law of the wall for a given structured surface. One can also modify the mixing length here, that instead of y plus, one would now take y plus plus delta y naught plus a divided by a plus, and likewise instead of y, we would take here y plus delta y naught, and delta y naught is correlated in this way by K's and Reynolds. This approach is no longer used now, but nonetheless it provided excellent measurements, excellent predictions, which compared with experimental data very well. Finally, we turn to near wall heat transfer, and like we developed the law of the wall for velocity from phenomenology, where we postulated u as a function of, here we will say T minus Tw, the wall temperature, is going to be a function of firstly y tau wall mu and rho, which really determine the four things which really determine the velocity profile. And in addition, now you will have a Q wall, because that would determine the temperature gradient at the wall. Cp is the specific heat of the fluid, and K the conductivity of the fluid. And therefore, if one carries out the dimensional analysis, one would find that a quantity T plus, quite unusual looking, but what you have here is a T plus equal to minus T minus Tw over Qw into rho Cp u tau. T plus would be function of y plus, Prandtl number, and Qw plus. Qw plus is really Q over rho u tau q, and that is really the effect of friction at the wall, which generates heat, but usually compared to the actual heat transfer, this term is very, very small, and therefore, it is not of great relevance. Effect of that can be taken up through property variations at a later time, but therefore, this term is really dropped, and we say that T plus will be a function of y plus n Prandtl only. So, let us see what is the form f y plus Prandtl will take in different layers of the inner layer. Now, to generate the T plus law, we first of all look at the differential equation, where we say that for a smooth impermeable wall at any rate, the convection term will be very, very small, and therefore, the total diffusion of heat flux would be equal to 0, or essentially Q total divided by rho Cp would equal Q wall divided by rho Cp equal to minus alpha dt by dy plus V prime T prime, and all this would be equal to a constant. In the sublayer, Q wall over rho Cp will be minus alpha dt by dy. Yes, Q in the laminar sublayer, Q wall over rho Cp would be equal to minus alpha dt by dy, and therefore, and Q wall is constant. So, if I integrated that, I will get T minus T wall equal to Q wall minus Q wall y divided by rho Cp into alpha. Now, if I said that the minus T minus Tw divided by Q wall divided by rho Cp would be equal to y by alpha, and if I divide this by u tau here, then this will be u tau, and this is nothing but the definition of T plus, and that will be equal to y by nu u tau into nu divided by alpha, and therefore, this is nothing but our y plus, and this is Prandtl number. So, in the laminar sublayer, it is straightforward to show that T plus would be equal to Prandtl times y plus, and Prandtl times y plus is also equal to Prandtl times u plus. So, laminar sublayer is fairly clear. Now, in the turbulent layer, which is characterized by 30 in a maximum of 30 and 30 Prandtl number, less than y plus and less than 0.2 delta plus, or the thermal thickness would be determined by the Prandtl number in the intermediate transition and sublayer regions, and therefore, we take maximum of 30 to 30 Prandtl to 2 delta plus, which is the end of the transitional layer. The relationship dt by dy would read as dt by dy equal to Q wall over rho Cp u tau equal to df by dy plus into dy plus by dy, which is u tau by nu, and this expression must be independent of nu, which gives me that df by dy plus must be equal to dt plus by dy plus equal to, now we say 1 over kappa t y plus, or T plus equal to 1 over kappa t ln y plus, all this for a fixed Prandtl number, and therefore, the constant of integration here C t would be a function of Prandtl number, and kappa t turns out to be kappa divided by 0.9 equal to 0.44. In the fully turbulent layer, you will again get a logarithmic law for the temperature. In the laminar sublayer, you will get this. The transition region is somewhat complicated, not easy to define, but the two laws that we have got, T plus equal to y plus into Prandtl for laminar sublayer, and T plus equal to 1 over kappa t times ln y plus Ct Prandtl for the turbulent layer. These two laws suggest that it is possible to generalize this as T plus equal to sigma times u plus Pf. Now, to understand this, consider the turbulent law, for example. The turbulent law says that T plus is equal to 1 over kappa t ln y plus Ct Prandtl, but u plus is 1 over kappa ln y plus c, which is our 5.4, if you remember. So, I can substitute for ln y plus here, then I will say T plus equal to kappa over kappa t u plus minus 5.4 plus C t Prandtl. Or another way of writing is k over kappa over kappa t into u plus another quantity called C t Prandtl divided by Prandtl t or kappa over kappa t minus 5.4 divided by kappa over kappa t. And if I were to call this quantity P f for the timing, then you will see this, and if I call this to be sigma, or then it will look like sigma u plus P f. Similarly, in the laminar sublayer, you had T plus equal to Prandtl y plus is also equal to Prandtl u plus. So, I can write this as Prandtl times u plus 0 and say that this sigma is now Prandtl number, the laminar Prandtl number. So, it is possible to generalize both these laws by an expression like so, T plus u plus P f, where P f and sigma take different values in different layers. So, we are going to say now that this kind of representation T plus equal to sigma u plus P f applies across from laminar sublayer onwards to fully turbulent layer, provided we we interpret sigma correctly and P f correctly. Now, sigma, which is kappa over kappa t, in a way represents, as you will see shortly, the slopes of the velocity and temperature profiles in the fully turbulent layer, and therefore, it would amount to essentially turbulent Prandtl number. And therefore, I have replaced kappa by kappa t by Prandtl t. So, P f for the fully turbulent layer would be that, whereas for the fully laminar sublayer, it would be 0 and sigma would be equal to laminar Prandtl number. So, for the entire layer now, entire inner layer, tau tot is equal to tau wall mu effective du dy, and q tot is equal to q wall minus k effective by dt dy. And therefore, if I define Prandtl effective equal to C mu effective by K effective, then it will simply amount to dt plus by du plus by the definitions that we have. To understand this, let us say Q wall is equal to minus Kt dt dy or K effective rather, which is K plus Kt, and tau wall is equal to mu effective du dy, which is equal to minus K plus Kt dt dy, and this is equal to mu plus mu t du dy. Then if I take a ratio of this, you will see I get Q wall divided by tau wall divided by rho, say I say this, then this will be rho here. So, tau wall divided by rho would be equal to minus K plus Kt divided by mu plus mu t equal to dt by dy into 1 over du by dy, and therefore, this will become Q wall divided by u tau squared equal to minus K plus Kt divided by nu plus nu t dt by du. If I divide this now by rho Cp, then I will get Q wall divided by rho Cp u tau squared will be equal to minus alpha plus alpha t over nu plus nu t dt by dy. I can write this now as minus dt divided by q wall divided by rho CPU tau is equal to so dt by dy divided by du by dy, so dt by dy divided by du dy, so dt by dy it will equal 1 over u tau into du by dy into du by dy into alpha plus alpha t divided by nu plus nu t, which is nothing but 1 over Prandtl effective. And this can be written as dt plus by dy, and this can be written as du plus by dy, and therefore I get the expression that dt plus by du plus equal to Prandtl effective, and that's what I've shown here. And therefore you will see here Prandtl effective is equal to dt plus by du plus, and therefore t plus would be 0 to infinity Prandtl effective du plus, and this would give us a continuous temperature law as a function of u plus or function of y plus, depends on how one wants to read it. And by comparison of this, if I compare this expression t plus equal to 0 to infinity Prandtl effective du plus with sigma times u plus plus pf, then I can show that pf would be simply 0 to u plus Prandtl effective divided by t Prandtl t minus 1 into du plus, where Prandtl effective is Prandtl times 1 plus nu t by nu plus 1 plus alpha t by alpha, and nu t by nu will be given by this. Why? Because remember tau wall is mu plus mu t du dy, and therefore tau wall over rho, which is equal to u tau squared, will be nu plus nu t into du by dy, and that will be equal to nu into 1 plus nu t by nu du by dy, and therefore you will see that if I 1 will equal nu by u tau squared into du by dy into 1 plus nu t by nu, and this is nothing but du plus by dy plus into 1 plus nu t by nu, and therefore you will notice that nu t by nu will be simply 1 over du plus by dy plus minus 1. So that is what I have shown here. So we say nu t by nu is equal to du plus by dy plus raised to minus 1 minus 1, and alpha t would be simply nu t divided by Prandtl t. This expression shows that, remember, du plus by dy plus is equal to 1 in the laminar sublayer, and naturally therefore this will be 1 minus 1. So in the laminar sublayer nu t by nu goes to 0, and Prandtl effective would simply go to Prandtl number. Yes, because that dt plus by dy plus there is equal to Prandtl number, and du plus by dy plus is 1. And therefore now the task is simply this: how do we determine pf as a function of u plus? Well, we need the values of du plus by dy plus. So either we can take them from the 3-layer law, or which applies only to smooth surfaces, or we can use the Van Dries mixing length model, so that we can also allow for pressure gradient and suction and blowing for du plus by dy plus, and use it here to integrate this expression to obtain pf as a function of u plus. So you will see that T plus, in a way, because of its definition, T plus, which is equal to minus T w rho CPU tau divided by QW, which I can also write as TW minus T into rho CPU tau divided by Q wall, or I can speak of this as 1 over rho CPU tau as H up to distance y. QW over TW minus T can be thought of as rho CPU tau divided by heat transfer coefficient up to distance y in a boundary layer, and therefore, T plus being inverse of the conductance can now be thought of as resistance to the resistance to heat transfer. And therefore, the relationship that we have, T plus equal to U plus PF multiplied by sigma, is really what it indicates is, since U plus is related to resistance due to momentum transfer and T plus is resistance to heat transfer, we can say PF is really the excess resistance over resistance to momentum transfer, and that is the interpretation one can now give to PF. PF will be equal to 0 for parental equal to 1 as a rule. What I have done is I have integrated using du plus by dy plus from Vander's mixing length model and found the following. So, for example, here is the value of PF and here are the values of U plus. Up to U plus equal to phi, you have laminar sublayer, and you do get the resistance to heat transfer is in excess of momentum transfer even in the laminar sublayer. And then this is at Prandtl number of 50, this is at Prandtl number of 5. At Prandtl number 1, there is no, it's all 0, there is no excess resistance, and as we observed earlier, you will have perfect analogy between heat and momentum transfer. For 0.7, which is air, you have negative PF, which means the resistance to heat transfer is less than the resistance to momentum transfer, and in liquid metal, the resistance is even lesser than that to momentum transfer. The transitional layer would occur somewhere around U plus of 13, end of transitional layer corresponding to Y plus of 30 would occur somewhere here, and from here onwards you have really fully turbulent layer. And it so happens that in the fully turbulent layer, the PF value reaches almost constancy, it remaining only a function of Prandtl number. So, we can say PF in the limit is always a constant for a given Prandtl number, and that these values of PF at large values of U plus have been correlated, and the most well known among these is PF infinity is equal to 9.24 divided by Prandtl t raised to 3 by 4 and into another function of Prandtl divided by Prandtl t. We can also interpret our CT Prandtl in this manner, and PF infinity would be Prandtl t CT Prandtl by Prandtl t pi minus pi by 4. This correlation for CT Prandtl was obtained by Russian scientists Kader and Yaglom, and it covered the range of Prandtl numbers from liquid metal range to very, very viscous oils. For rough surfaces, PF infinity is given by both by Dupree and Sebersky and also by Jaitilake, who gave this formula, and therefore I have given here the references to both of them. For a rough surface, it is 5.19 Prandtl raised to 0.4 YR equivalent roughness height raised to 0.2 minus 8.48. Jaitilake's formula requires experimental information on A, which is meant essentially for structured surfaces. So, with this I end the lecture which covered the topics of transition, it covered the topic of temperature law, and we found that a continuous temperature law is also possible to be derived for the inner layer.